Forces, Part 1. Newton's three laws. Here you see a picture of Newton, and you see one of his famous books. He actually published a number of books, and in physics we talk about the three Newtonian laws that he established, but he established many principles for physics and for math and for observations about the world and the way optics work and light and a lot of things. And many of his ideas stood for over 200 years before being modified or added to. Now we know that as things approach the speed of light, some of these laws break down, but for things that move slowly on our scale, these laws work extremely well. And you can see that he thought of some of these ideas and published them in the 1600s, so he was ahead of the curve. So the first law, this is inertia. So we can define this as an object at rest stays at rest, and an object in motion stays in motion with the same speed in the same direction unless acted upon by an unbalanced force. In other words, resistance to change. Whatever it's doing, it wants to keep doing, unless if a force, an unbalanced force, acts upon it. So you can see, for example, in this animated GIF, you can see the car, and you can see the man if you don't wear a seatbelt, and if the car runs into a wall and you're not wearing a seatbelt, you are not staying in the car and you will be flung from the car. This has actually happened in many pretty bad accidents where people fly through the windshield or fly through the different parts of the car. And you can see another example of that over here on the right. In this case, these look like oxygen cylinders that were being carried in maybe an SUV, and they weren't strapped down. Obviously, there was some sort of accident, and they kept going. And if you've probably seen this done, where you have a tablecloth and you have things on top, and if you can pull the tablecloth fast enough, the settings on top won't move. They're not in motion. They want to stay still. So, mass is the measure of inertia. The greater the mass, the greater the inertia. Meaning, the greater your mass, the more you want to keep whatever you're doing. Which is why semis or tractor trailers can be very dangerous on the road, because they can't do emergency stops very quickly. So if you're in front of it, it's very likely that they will run into you in an emergency stop. Whereas a motorcycle can stop very quickly because it has a very small mass, meaning it has relatively low inertia, which allows it to change its velocity very quickly. And this was a fun video that I found. It is a Jenga pistol. So you can see it working here. Hopefully. And you can see through this video that this guy who made the Jenga pistol, he was able to move individual blocks without disturbing what was on top because of the inertia of those blocks. So that's the first law. The second law, we can summarize it as F equals ma, and we can write this in a couple of different ways, which I'll show you in a little bit. And the way we define this is when the net external force, sigma F, acts on an object mass of m, the acceleration a that results is directly proportional to the net force and has a magnitude that is inversely proportional to the mass. This sigma just means the sum of all forces, or this sigma just means the sum. When we have sigma f, the sum of all forces, and that's going to be equal to the mass times acceleration. And this is the net force. So this would be, once you account for all of the forces, you find what the final force is, and that's going to be equal to the mass of the object times its acceleration. So the way to look at this flowchart, if you have unbalanced forces, that means that you will have an acceleration, because if you have a net force, sigma f, that means that your mass will have an acceleration. This acceleration depends directly upon the net force, which means as the net force increases, I'm going to use a different color for this, as the net force increases, the acceleration also increases. Now, as the mass increases, so if we were to compare like the elephant to whatever it might be compared to, in this case a feather, the acceleration depends inversely upon the object's mass. So given the same force, if your mass increases, the acceleration will decrease. And we'll go through some practice for this in a separate video or in class. And that is Newton's second law. Newton's third law, equal and opposite. You've probably heard this said before. For every action, there is an equal and opposite reaction. This understanding actually permeates through a lot of physics and through a lot of things that we do day to day without even realizing it in some cases. And so for the first picture over here on the left, you see this, well, let's say that this is you on a skateboard, and you are pushing against a wall to propel yourself in a certain direction. If you think about it, the direction that you are pushing on the wall is in the opposite direction of the direction you want to go. And in fact, you can think of the wall as pushing against your hand, and that is what is propelling you. It's equal and opposite. However hard you're pushing against the wall is how hard the wall is pushing against you. Unless, of course, you were to break the wall. If you look at this picture over here on the right, you can see there are two people here, and they each have a scale, and the scales are attached by a rope. And if both of these people pull on the scale, there's no way for either of the scales to read a different value until one person overpowers the other. So until that point, it's going to be equal and opposite. And these scales will read the same. And in fact, you can go even one step further and you can think of the shoes that they're wearing. And if they are pulling on these scales, the shoes are exerting a force on the ground, gripping, that keeps them in place with the exact same force. And we can keep going with this understanding. If you are sitting in a chair, why don't you fall through the chair? You're putting weight down on the chair. The chair is pushing up on you. And if we go one step further, why isn't the chair accelerating towards the center of the earth? It's because this chair is on a surface, or we can just say on the surface of the earth. The earth is pushing back up on the chair with the exact same force that the chair is pushing down on the surface of the earth. And when you sit in this chair, you're adding to the weight. The surface of the earth also increases the force that it applies back up to the chair, and the chair applies a force up to you to keep you in equilibrium, to prevent you from accelerating. It doesn't have a greater force, because then you might be accelerated into the air. You might think you might float in the air. It keeps you in place. The earth is pushing back up on you. In fact, if you think of the way your bathroom scale works, when you step on the scale, you are pushing down on it. Your weight is pushing down. The way your scale reads your weight is by how much it has to push back up on you to balance your weight out. Oftentimes, for the older scales, they use springs, and the springs would, as they compress, they apply a force back up to you, and wherever that is in equilibrium, it shows you that reading. And if you think of spaceflight and of these rockets, I think this is a Delta IV medium rocket, you can see the exhaust on the bottom. And if you think on the most basic level, the way these rockets work, it isn't exactly through ignition and through combustion necessarily. It's really that it's throwing a tremendous amount of mass downward, and because it's equal and opposite, throwing a bunch of mass and particles and atoms as forcibly as you can downward causes you to go in the opposite direction. It's equal and opposite. In fact, in space where you don't have oxygen, this is the way the rockets still work. They essentially are throwing out mass in one direction so that it pushes them in the opposite direction. Equal and opposite.